Hello, welcome back to our channel. And on your screen, we have come up with a different topic today. It is related to the oscillator. So if you recall from our previous model, we talked about an oscillator, what it is, its operating principle, how it works, and we also discuss what we need to do in electronic design in order to have the oscillator circuit work, such as the condition for oscillation. So when you design an electronic oscillator, you have to satisfy a Barkhausen criteria that says there are two conditions about the loop gain magnitude and loop gain phase. And now we have to talk about, in the category of oscillator, there is one category or one type of oscillator called as a phase shift oscillator. So we will see why it is called as a phase shift oscillator. But before that, let us recall few concepts about the feedback system, and then we talk about the positive feedback and the negative feedback, and after that, we say how the circuit can act as a negative feedback circuit or a positive feedback circuit. And based on that, we'll see how the oscillations are produced and sustained. So if you recall, we basically have this gain block here, and we have this feedback network actually, okay, feedback network. So we will say that this gain block has open loop gain AOL, and the feedback network has a gain of beta, and you have an input to this network, and then you have output of this network. So this is basically an open loop system in the top. Okay, and then what you do is take the portion of it, the output, and which becomes an input to the feedback network. And the job of the feedback network is provide a gain which is less than unity, so that the output of the feedback goes and gets mixed here with the input. So here you can say that this is your input, actually the main input, V in. So see the difference. I'm calling it V in, and here the input that the gain block receive is VI, and here the output of the feedback network. And here we say that this is positive or negative. So it depends on whether the feedback signal is getting mixed with the input in a positive way or in a negative way. We call it as a positive or the negative feedback. So if the feedback signal gets subtracted from the input, so that V in is positive and the feedback signal is in opposite phase, that is here is you have a negative, then we say the feedback is negative. However, if the feedback signal is getting added along with the input, so that Vi becomes V in plus Vf, and here is your Vf, which is beta times V naught. So beta is the gain of the or the attenuation factor of the feedback network, and of course VO is what you feed here, so that becomes here. So based on that, we saw that there is a transfer function, let us say VO over Vi, and take a magnitude of it, and we say this is AOL divided by 1 plus minus AOL times beta. So that's our final transfer function. So from this equation, we understand that, okay, this is your open loop gain and this is your feedback factor. So beta is usually less than 1. So that's why we call it as an attenuation block. And here we call it as a gain block actually. Okay. So from this equation, we want to understand what is the meaning of this equation. So if your feedback is negative, this equation is AOL divided by 1 minus AOL times beta. And if the feedback is positive, this equation becomes AOL divided by 1 plus AOL beta. So after solving the equation around the loop, we have come to derive this equation. So if you are new to this module and you want to understand how we derive this equation, please refer back to our earlier modules on the oscillator basics, the definition of oscillator, the Barkhouse criteria, and all that. So if you have a negative sign here, then it's simply an amplifier with a negative feedback. But if you have a positive sign here, you can have a positive feedback. So when you have a positive feedback, you want to make this system oscillate. It means you want to produce a sine wave or square wave or triangular wave or sawtooth wave, any kind of wave function. You want to make sure that your feedback gain is less than 1, and the product of this A times beta has to be greater than or equal to 1. So let me write here. So what you will do is right here, you will say that your AOL times beta has to be greater than equal to 1. And obviously your beta here is always less than 1 because the feedback network is basically an attenuator. Okay, it is taking the fraction of the output feeding back to the input. So that's why it is less than 1. So let me write it properly so that you can actually see that. So beta is less than 1. And when you have this first condition satisfied, the second condition says that the angle of AOL times beta is exactly 0 degree or 360 degree. Okay. So which is basically 2 pi radian, 2 pi radian. So when you have this kind of conditions, the condition number 1 and the condition number 2 satisfy, we say that the circuit will produce the oscillation and the circuit will start oscillation and it will sustain the oscillation as long as you are meeting these two conditions. So how to understand that? So what happens, you for the feedback oscillator, when you have a positive feedback, you actually disconnect this external input source, and only circuit that you have is right here. Let me draw here. So only circuit you will have here, you have a gain block, and then you have an output, and then you have this feedback network, of course, and then output is connected to the feedback network, and you have removed the external input, so it becomes your input. Actually output becomes input here, and that's how this feedback signal output VF becomes the input to the oscillator circuit, and you have this sine wave produced, provided you are satisfying these two conditions here. Okay. And so what happens? You don't have any external signal as shown right here. So how will the circuit will oscillate without any external signal? So answer is, when you switch on the DC power to the circuit, in this case, there is a little bit noise in this electronic circuitry. For example, we are going to explain this circuit. So you have a transistor, you have a passive component such as a resistor and a capacitor. They have their inherent noise. So that noise is getting amplified here with a high level through the gain block. And the job of this network is to act as an attenuator, as I said, because it is reducing the output signal and taking only a fraction of it back to the input. But at the same time, based on the values of the passive components that we use to construct this feedback network, for example, it is made of RC components, resistors and capacitor. It is made of L and C, the inductance and capacitance. So that's a tuned circuit. So based on those values, there is a frequency of oscillation or frequency of filter actually. So those network are composed of RC or LC makes up a filter. So that filter's job is to only select a single frequency that is coming to it. as an input and filter it out and give it back for further amplification. And this process continues. So if you have made sure that your AOL times beta is greater than equal to 1 and AOL times beta, angle of AOL times beta is exactly 0 degree, you will have oscillation produced, and then over time they will if the gain is greater than 1, so the oscillation start and it grows and then it saturates to a steady state level, because the circuit's gain saturate so that AOL times beta becomes exactly 1. However, and of course the phase shift around the loop is 0 degree. However, you will not have sustained oscillation, or your oscillation will start and it will eventually die if your gain is less than 1. Okay, it drops to less than 1. Of course, if the phase is not exactly 0 or 360, you don't have any oscillation. So having said that, now let me talk about this circuit, which is the topic of today's discussion, phase shift oscillator. Okay, so phase shift oscillator, what we are doing, we are using a BJT or simply a transistor. We can use BJT or FET to construct this circuit. So you have already understood from our previous model, this is a BJT, this is the load of the transistor RC, that is the collector resistors. RB is used to bias the transistor at in an active level, in an active region, so that it can be used as a small signal amplifier. This is the DC power, VCC, and that's it. You have this circuit acting as your small signal amplifier. So imagine you don't have this network for a moment, so you apply at this node, at this point, you apply an external small signal AC voltage source, and based on the transistor which is biased in common emitter mode, you will have an output and amplified signal. So it would look like this. So you have like small signal input, of course overriding the DC level set by the VBE here, and you at this node you will have an amplified version. But look at the phase shift here. Here the output, here is the output, here is your input. Your output is exactly 180-degree phase shifted to the input. So we just recall from our previous discussion right now here, right in this model, we talked that the phase shift has to be 0 degree or 360 degree, that is 2 pi radians. So how to add another 180-degree phase shift? So idea is to, you can have one more amplifier stage right here, okay? But there is no feedback. You can add one more common emitter stage here and again invert this output to get a 360-degree phase shift. So your output will be in phase with this one. But where is the feedback? Without a feedback, you don't really have any oscillation criteria, because the phase shift around the loop, there is no loop. It is still an open loop circuit. For a oscillator, you need a closed loop circuit. So what we have done here, from this output node, you actually can give this fraction of output and to the feedback network, right? So in this block diagram, you can see that this is the gain block right here. This is your gain block. So let me clear this drawing first. And so again, this is your gain block. So it is this block, and this is your feedback network. So right here, this is your feedback network. So what you are doing here, you are feeding the output back to the input. So you are also feeding the output back to the input, and your feedback network consists of combination of capacitance, resistance, capacitance, resistance, capacitance, resistance. So, and again at here you have input, that is here. This resistor RS is just to use to isolate the circuit from the external load. Okay, here is your load. that you are giving the current. So again, so 180-degree phase shift is provided by an amplifier, and each section of RC provides a phase shift of 60-degree, right? So you have a kind of, this is actually R and then C, and no, this is not an R. So this is your RC. This is your RC actually, and this is maybe RB, and C is providing another 60-degree. So total phase shift by the feedback network is 180-degree. By the amplifier, it is 180-degree. So total becomes 360-degree. Okay. So after having said that, we just said that the feedback has to be designed, the feedback network has to be designed so that it acts as an attenuator. So the gain of the feedback network is less than 1. Okay, so this feedback network is designed in such a way that it has an attenuation factor of 1/29. So that's the standard one. And we just said that, so A times beta has to be equal to greater than or equal to 1. Okay, so A times beta is equal to 1. So if beta is equal to 1/29, the gain has to be 29. So that your BJT must have a gain of 29. Your amplifier section must have a gain of 29, so that your A times beta becomes equal to 1. Exactly. The first condition and the second condition we have satisfied. The first condition is about gain. Second condition is about phase. Okay, so how to design this circuit? Just select all values, register R1, R2, and R3 equal, and call it R. Select all the values of the capacitor C1, C2, and C3 equal, call it C, and then this is your approximate frequency of oscillation formula, which is frequency of oscillation is equal to 1/2 pi RC square root of 6. So for a given value of capacitor, calculate the value of resistor for a given frequency of design. Okay, so just put that value and make sure that your circuit will then oscillate. It will reach the steady. As soon as you switch on this DC voltage source, your circuit should start actually and then sustain an oscillation. So if the initial gain is greater than 1 actually, so the oscillation will start and starts growing, and then it will sustain and saturate to a constant level. So that's because the circuit's gain will saturate, so that A times beta is exactly equal to 1. How about we design this circuit using the FET? We don't want BJT. So yes, you can do it using the FET also. So here you can see the FET has been used. Exactly, it's a typical common source amplifier, CS. You have a drain resistor, you have a source resistance. This is emitter degeneration resistance in the BJT, but here it is called as source degeneration resistor. The role of this resistor is to provide the bias stability against the operating point variation due to temperature, noise, distortion, etc. CS is the bypass capacitor. So at the lowest frequency of interest, this acts as a short because its reactance is very low, and it improves the gain at the high frequency also. These CC and CC here are the coupling capacitors. So depends on the frequency range, you have to select their values in such a way that for an entire frequency range, they act as a short circuit, couple the AC input to the circuit, couple the AC output to the load. And R1 and R2 are used for biasing to provide a stable operating point here. The operating point, not the stable, but operating point. Stability is provided by this resistor. So again, you have a DC voltage source, and this circuit is basically your common source amplifier. You have a small signal input at the input side, and you have phase shifted 180 phase shifted output due to amplifier. That's why we say 180-degree phase shift output. Okay, this is the amplifier gain, which is the ratio of VO over VI, and here is your output will look like. Now what you do? Take the output and feed it to the feedback network. So here is your feedback network, the again combination of R and C, and that's why we are calling it as a phase shift, because we have got the 180-degree phase shift here from the amplifier, and we want phase to be shifted for another 180-degree, which is done by this RC network. That's why we call it as a phase shift oscillator. So 180-degree phase shift due to the feedback here, RC phase shift network, and output of the feedback network is becoming an input here. So from the block diagram, can we write here something like this? So let's say you have output here. This output becomes input to the feedback network. Gain of this network is beta, and it is less than 1, so that the design of the values of C and R are chosen such a way that beta factor, which is attenuator actually, is less than 1. Here you have a feedback output VF. VF is equal to beta times V naught. Okay, and then VF is actually getting coupled with your input here, right? VI. Okay, mixed up. So you have to make sure that this the loop A times beta angle, A times beta. A is the open loop gain, is 0 degree, and the magnitude of A times beta is greater than equal to 1. Okay, so that's it. So again, here also you will choose the resistance value to be equal, capacitance value to be equal. Oscillation frequency is the same as in the previous case. For a given value of frequency and the capacitor, for example, you can select the value of resistor, calculate it, and put it and design the circuit. So again, here also each RC section will contribute 60-degree phase shift. The feedback network has a attenuation factor of 1/29. The FET then must have a gain of 29. Okay, so what is the gain of the amplifier here without the load? It is GM times RD. So GM is the transconductance of the FET. In the case of previous slide, the BJT transconductance is GM. So gain of that amplifier was GM times RC, where RC is the collector resistance. So we have seen how to build and design a phase shift oscillator using BJT, phase shift oscillator using FET. What about using the operational amplifier? So here you see that what you do, you have an op-amp with the open loop gain AOL. You can see that I'm using an inverting configuration of the op-amp. So you got the VID here. Here you have a VID, which is the difference between the two inputs, actually V1 minus V2. And V1 is the voltage here, V2 is the voltage here. And due to virtual ground concept, this V2 bias, which is at 0, comes at the V1, and the amplifier's action, negative feedback action in such a way that it makes the two voltages at equal potential. So V1 also tries to get forced to the 0 volt. Now RFB and R1 are there to set the gain of the amplifier, which is RFB times R1, RFB over R1. So that's the gain. That's the negative feedback amplifier gain. And the phase shift due to amplifier is 180-degree. So the remaining phase shift has to be provided by this guy actually. So you can see that the feedback network will provide the remaining 180-degree phase shift. Again, you have the same formula R1, R2, R3. You have the C1, C2, C3. Frequency of oscillation is required, let's say 100 kilohertz. Then you choose the value of 0.01 microfarad, calculate the value of R from this formula and put in the values here, and your circuit will oscillate as long as you will satisfy the two condition of A times beta magnitude. A times beta has to be greater than equal to 1, and angle A times beta is equal to 0 degree. So again, the same condition here. Each RC section contributes to 60-degree phase shift. Feedback network has an attenuation factor of 1/29. Op-amp must provide the gain of 29 then to compensate this loss. Okay, and so that loop gain becomes 1. Now, let me take you the special circuit, which is called as twin T oscillator. So look at this circuit configuration. So here you see the operational amplifier V1 and V2. You got the output and it is fed back to the input through this network, the twin network. So it's basically a negative feedback because this output is applied to the negative pin of this. And there is one more feedback which is getting here to the positive pin of the operation amplifier R3, R4. So two kinds of feedback here. So what we see here, two T sections. So here is the T, one T, and here is another T, and here is a common point. So one T is called as RCR. Second T is composed of CRC. So first RCR, that acts as a low pass filter. This network is acting as a high pass filter. So together they are forming a bridge which is kind of tuned at a desired frequency of oscillation. So let's say you choose the ratio of the capacitor in such a way that C2 over C1 and you call it as a X. So here C2, here C1. And that ratio you make equal to the ratio of two resistors R1 and R2, R1 and R2, and you call it again X. So if your X is equal to 2, so that let's say C2 is 2 times C1 and R2 is 2 times R2, so it is essentially an amplifier with a negative feedback. That's it. So this is how it will act. However, if your X is greater than 2, so let's say C2 is larger than C1, so that X is greater than 2, and R1 is greater than R2, so that X is again greater than 2. In that case, this amplifier becomes an oscillator, and you can have a sustained oscillations at a desired frequency determined by this formula, which is 1 over 2 pi RC. So choose the values of R and C, and you get for a given frequency of oscillation, choose the value of C, calculate the value of R, and then you will have sustained oscillation. So hope you understood the concept of phase shift oscillator, what it is, how the feedback theory is applied, how we satisfy the loop gain and loop phase criteria. And we saw the different versions or variations of phase shift oscillators such as BJT, FET, operational amplifier, and we saw special oscillator called as twin T oscillator using op-amp. So if you like this module, click the like button, put some comments as your opinions about what you think, and subscribe to the channel. Share this module with the audience for wider reach. And till then, stay tuned for more informative contents like this. Wish you happy learning.